Okay, so with chapter 4, we're going to be looking at solutions. We'll continue to look at reactions. So we'll continue to be able to use stoichiometry to kind of relate any two substances in a reaction. We'll see as we go through this chapter. There'll be a couple steps that are a little different with that process, but the general idea is going to be the same. But before we do that, we should look at what solutions are in general. And if we look at the picture here, this could be an example of some sort of copper solution just based on the blue color. But with it, and with any solution in general, we'll have two basic components. We may have multiple of the solutes, but we'll have two basic components, and the solute is just going to be the substance that we're dissolving, and then the solvent is going to be the substance that we're dissolving it into. So for the most part, when we're looking at solutions, water is going to be the solvent. It doesn't always have to be in organic chemistry. They use a lot of organic solvents, so things like ethanol, ethyl acetate, hexane, acetone, substances like that. But for the most part, with us, we're going to be looking at water as the solvent, and then the solutes would just be things like copper, sulfate, or whatever is going to be dissolved in this solution. If we were looking at something like a saltwater solution, the salt itself would just be the solute, but that's going to be the substance that we're dissolving. And then with these solutions, we're going to be referring to them as homogeneous mixtures. And that just means they're going to be uniform throughout. So we're going to see once we actually dissolve a substance, we're not going to have that located in just one spot within that solution. It's then going to just spread out to be even throughout the entire thing. And when we actually do take a substance and dissolve it, depending on what type of substance it is, that process actually looks a little bit different. But when we're looking at ionic substances, so something that's going to have a positive and a negative charge, and then those opposite charges attract, and that's what's actually just holding the substance together. But when we take those ionic substances and dissolve them in water, we're going to see those ions do what's known as dissociate, which essentially just means that they're going to get separated. And we can see it with the image here. So we've got some ionic substance shown with the negative green ions, the positive purple ones. But when we take that substance and dissolve it in water, now we're going to have these water molecules essentially rip those ions apart. And that's why we can see in the top left here, we've got a positive ion, and the top right, we've got a negative one. And then depending on the charge of those ions, what we're actually going to see with the water molecules is they're going to arrange themselves in a specific way. So with these water molecules, they kind of look like a Mickey Mouse head. In the middle, we've got the oxygen, which is going to be slightly negative. And then the ears of it, that the hydrogens, those white or gray, are going to be slightly positive. So if we've got a positive ion here, just think about opposite charges. Positive is going to attract negative. So that's why we see the water molecules here all having the negative hydrogens in red, being closer to that ion. And then we see just the opposite for the negative ion here. Now it's going to be more attracted to the positive hydrogens. And that's why we see the white or the gray ends of those water molecules now surrounding that negative ion. And then depending on if we do see ions produced when it's dissolved or not, that's going to determine if it's an electrolyte. So if you've ever heard or ever seen the Gatorade or the Powerade marketing, a lot of the times they reference electrolytes as a way to better hydrate, a way to improve your athletic performance. And we're actually looking at the exact same things here. So these are just going to be ions in solution. So with the electrolytes in those sports drinks, typically they're looking at things like sodium ions, chloride ions, potassium ions. With us, it's just going to be any ion in solution. But if we do have those ions produced when we would dissolve a substance, that'll be an electrolyte. And if it just stays as the intact molecule, so something like sugar isn't actually going to get broken apart into carbon and hydrogen and oxygen ions, it's just going to stay as that sugar molecule. So that would be an example of a non-electrolyte, just because it's not going to it's not going to get broken apart into those ions. It's not going to dissociate. So if we look at the table here, we've got strong and weak electrolytes and a non-electrolyte. So a non-electrolyte, we'll see on the next one, is basically just going to be most molecular substances. But the difference between a strong and a weak electrolyte is just going to be the degree of that dissociation. So with a strong electrolyte, we're going to get basically 100% ions when we dissolve that substance. Whereas a weak electrolyte, we'll see most of that substance is actually going to stay intact when we dissolve it. We'll only get a few ions being produced there. And when we're looking at the ionic substances, for the most part, these are going to be strong electrolytes because for the most part, ionic substances dissolve very well in water. So they're going to produce a whole bunch of ions. And then we'll also see the same thing with strong acids and strong bases. So there's actually a reference table we have for this chapter that lists all the strong acids and strong bases. But then with the weak electrolyte, we'll see substances that are going to give us a few of those ions, but not a whole bunch. And then, like I said, the non-electrolytes, where it stays is that intact molecule. Those are going to be our molecular or covalent compounds, with the exception of acids and bases. So again, this will be something like sugar or carbon dioxide even, because those substances can dissolve, but they're not going to produce any ions when they do that. So they're not going to be electrolytes because of it. And then whether or not a solution is an electrolyte dictates some of the properties of that solution. And one of those properties is going to be the ability to conduct an electric current. So with the images here, we can see a non-electrolyte on the left, a weak electrolyte in the middle, and a strong electrolyte on the right-hand side. And in each case, we're using that solution to attempt to essentially just close a circuit hooked up to a light bulb. So we can see with the non-electrolyte, and they're showing it with the little diagram here. We don't get any light produced from the bulb, because with the non-electrolyte, we don't get any ions produced in solution. And it's going to be those ions that can actually conduct that electric current. So since we don't have that ability to conduct an electric current, we don't see any light produced. And then with the weak and the strong electrolyte, we do have some of those ions. So we see in each case that the light turns on, but it's much dimmer with the weak electrolyte, because as they're shown in the diagram here, we're only getting a few of those ions. So we've got 6 molecules in total, but 4 of them are still intact. 2 of them dissociate into the positive and the negative ions, but 4 of them are still intact. So we're considering it a weak electrolyte just because we only have partial dissociation. So we can only conduct a small current through that solution. We only get a little bit of the light produced as a result. Whereas the strong electrolyte, we get much more of that dissociation. We essentially get full dissociation. So now we've got a whole bunch more ions. We can conduct the electric current much better. And that's why we see a much brighter light being produced here. Right. And then with the electrolytes, like I mentioned, if we're trying to identify specifically what type of electrolyte a substance is, we've got a couple tables that'll help us out with the acids and the bases. We've got just a few strong acids and just a few strong bases. Anything that's not included on this list would just be considered then a weak acid or a weak base. So if we look at HCl here, hydrochloric acid, the reason that's going to be considered strong is because when we take that hydrochloric, the HCl molecule, and dissolve it in water, it's going to fully dissociate into hydrogen ions and then chloride ions. Whereas if we had something like hydrofluoric acid, so replace that chlorine with a fluorine, we're going to have most of that molecule stay intact. So we'll keep the hydrogen and the fluorine bonded together, while only getting a little bit of dissociation, only producing a little bit of the hydrogen ion and a little bit of the fluorine. And then the same thing with the bases on the right-hand side. So group 1 hydroxides, some of the group 2 at the bottom of that group will have full dissociation with these bases. So it's something like sodium hydroxide will get full dissociation into a sodium ion and a hydroxide ion, whereas something like magnesium hydroxide, group 2, higher up in group 2, most of that substance is going to stay as the magnesium hydroxide, and only a little bit of it is going to dissociate into the magnesium and then the hydroxide ions. And that's why we would consider magnesium hydroxide weak, while considering the ones listed here to be strong. And then with the ionic compounds, like I mentioned, typically ionic compounds will dissolve because like dissolves like. So since water is polar, it'll be good at dissolving other polar substances. But there are a few exceptions. So if we look at our solubility table, excuse me, the ones at the bottom, insoluble, just means it won't dissolve. So if we've got something that contains a sulfide or a carbonate, phosphate, hydroxide, typically compounds with these ions in them won't dissolve, but there are a few exceptions. So like we already saw with the hydroxides, we do have a few strong bases here. And then just the opposite at the top here, these are all going to be substances that typically dissolve. Nitrate and acetate are always going to, but these are going to be substances that typically dissolve. And then with chloride, bromide, iodine, and sulfate, there are just a handful of exceptions. So if we've got chloride, typically that's going to dissolve. But now if we've got it with a silver plus ion, a lead 2 plus ion, this dimercury, divalent ion, any of those are going to be exceptions, which means those actually wouldn't dissolve. Those would be insoluble. And then, like I mentioned, with this chapter, we're going to continue to look at solutions, or continue to look at reactions, excuse me, but specifically with reactions and solution. And we're going to see a lot of the times these reactions can be classified as metathesis reactions or exchange reactions. Sometimes they're also even known as double replacement reactions. But essentially what these are going to be looking at is taking two solutions. And with something like the example we have here, silver nitrate and potassium chloride, we get two ionic compounds in solution. So we'll have a positive and a negative. And what we'll see on the right-hand side is the ions, the charges we have on those isn't going to change as well. So potassium is still going to be +1, nitrate still -1, same thing for silver and chlorine. So with these reactions, we're essentially just taking the different ions and switching what they're with. So we're taking the positive from one, combining it with the negative from the other, and then just doing the same thing with the remaining pieces there. So in this case, potassium goes with nitrate. And then depending on exactly how this occurs, we can have a couple different sort of further classifications. So the one we were actually just looking at is a precipitate or a precipitation reaction. In some cases, we'll form a soluble non-electrolyte, so something that actually won't be able to conduct electric current through it because it's not going to have the ions there. And then in other cases, we'll be producing a gas. So with these precipitation reactions, if we go back for a second here, we're taking two solutions, mixing them together, and we'll have all of these ions. So we'll have silver ions, and nitrate ions, potassium ions, and chloride ions. We'll have those all dissolved. We'll have all those dissociated. But then when we mix these two solutions together, we'll have all of these ions start bumping around. And then in the case of silver and chlorine, when those bump into each other, those are actually going to form an insoluble substance. So we'll actually see a solid gets produced here. And that's what we're going to be referring to as the precipitate. So if we look at the picture here, this would be a, just based on the color, some sort of lead precipitate. So we've got a lead, could be lead nitrate, lead, whatever it's going to be for this solution. But we've got those lead ions. And then we've got maybe some sort of chloride solution here. So when we have the dissociated lead ions combined with the dissociated chloride ions from those separate solutions, now they're going to combine. The opposite charges are going to keep them together, and it's just going to form an insoluble substance, and that's why we can actually see the solid getting produced here. So again, the solid being produced is known as the precipitate, and these are just known as precipitation reactions. So if you think about precipitation in the environment, rain or snow coming down, we can kind of think of the precipitate itself in a similar manner. We're going to mix these together, form that solid, and then if we just leave this beaker sitting here, we're going to see that solid just sort of float down to the bottom and just settle there, similar to just snow or rain falling from the sky. And like I mentioned, the solid, the insoluble solid is going to be the precipitate. So insoluble just means it won't dissolve. Soluble means it will. And that solubility we'll come to see is going to be based on a few different factors. And then solubility referring to how much of that substance can dissolve. But that's going to be based on factors like what we're trying to dissolve it in. So depending on what that solvent is, certain things will dissolve well in one substance and not dissolve at all in another. So the solvent is going to be important, but we'll also see the temperature has an effect as well. So typically we'll see as the temperature increases, solids and liquids, the solubility is going to increase, but we'll see with gases, it's just the opposite. And then with these solubility rules, we've already seen we have the solubility table for those ionic substances. So we don't really have to memorize these rules at all. We just have to know how to use that table. But we just want to recognize that certain substances are always going to be soluble. So sodium, nitrate, chlorate, perchlorate, acetate, ammonia, potassium are always going to be soluble when we've got them in an ionic compound. And then there are other things that are typically soluble, but with a few exceptions. And then just the opposite, there are others that are typically insoluble, but then a few exceptions as well. And then when we're looking at writing these equations, there's what's known as the molecular equation, which is similar to what we've already seen, where it just shows the complete formula for all of these different substances, as well as the state of matter. And then if we look at it, we've got the coefficients still, just to make sure we're conserving mass. But with these reactions, we're also having to conserve charge as well. So that's why if we look at it, none of these have a superscript, so none of them have a number to the top right, because all of these ionic compounds are going to be neutral overall. So we've got a neutral charge on the left, a neutral charge on the right. So we're conserving charge in addition to conserving mass. So we've got 2 potassiums, we've got 2 iodides, 1 lead, and 2 nitrate. So we're conserving mass. We're also conserving charge with the molecular equation. But we can take these reactions, and then for the aqueous substances, those strong electrolytes, we can actually show them as the dissociated ions. And that's what we're looking at with the Ionic equation. Excuse me. So like I said, it's the same equation. Now we're just showing those solutions as the dissociated ions. So this Ionic equation gives us a better picture of what's truly happening there, because with lead-2 nitrate or potassium iodide, the potassium nitrate solution that's being formed, we don't actually have those substances as a lead-2 nitrate molecule or a potassium iodide molecule. Now we've got them as the dissociated ions, and that's what this Ionic equation is reflecting, the true nature of those substances. And then if we look at this equation, we'll see there's certain pieces that don't change at all. So we've got NO3 and potassium on both sides, just as the dissociated ions. So what we can also do is take this Ionic equation and remove those substances that don't change at all. Those are known as spectator ions. We can remove those pieces that are the same on both sides, and then just focus on what actually is changing. So in this case, we're taking lead iodide, or lead and iodine ions to form lead-2 iodide, the insoluble precipitate. So with our net Ionic equation, we can just focus on the pieces that are actually changing. And if we look at the net Ionic equation, we've got 1 lead, 2 iodides on both sides. The right-hand side is neutral. The left-hand side, we've got a +2, but that's balanced out by 2 -1 charges. So we've conserved mass, we've conserved charge with the net Ionic equation. And if we go back and look at the full Ionic equation, we'll see the same thing. So we've still got 1 lead, 2 iodides on both sides. Now we've got 2 potassium, 2 nitrates on both sides as well. But if we look at the charges, neutral, and then +1, but we've got 2 of them. +1 or -1, but we've got 2 of them. So the right-hand side still balances out to neutral. And then the same thing if we add up all of these charges from the left. So with all of these reactions, we're still showing the same thing. We're still conserving mass and conserving charge. We're just focused on sort of different information in each case. So in some cases, we may be interested in one version of these equations over the other, but they're still essentially all just showing us the same thing. And that's why they're still all conserving mass, conserving charge. So with these, if you do have to get the net Ionic equation, the first thing we're always going to want is just the balanced molecular equation, so the complete equation that we've kind of already seen. And then once we have that, we can look to see of our solutions, which of those is going to be a strong electrolyte, which of those is going to fully dissociate, and then we'll break those substances into the individual ions. And then we'll just look at both sides of a reaction, see what we've got the same on both sides, and just remove those substances, remove those ions or species, to just show what's actually changing, and that'll give us the net ionic equation. So with these, if we've got a solid, a liquid, or a gas, we won't break that into ions. But if we've got a strong electrolyte as a solution, that's where we'll actually have it dissociate, and that's what we'll show with the ionic equation. So if you want to practice with these two, you can. Again, we want to get the molecular equation, so we need to actually predict what the products are going to be. But these are going to be metathesis or double replacement reactions, meaning we're just taking the positive piece, combining it with the negative from the other compound, and doing vice versa. So in this case, we'll take the barium, combine it with sulfate, do the same thing with sodium and chlorine. But when you do this, make sure you consider what the charges are rather than just taking these pieces and combining them as it is. Because with the sodium and the chlorine, for instance, we don't want to just say, okay, we've got 2 sodiums and 2 chlorines. They're going to combine to give us a formula of Na2Cl2. We want to look to see sodium is going to be +1, chlorine is going to be -1. So we'll have NaCl, and then we'll need a coefficient of 2 in order to get it to balance. So with these ones, if you're predicting the products, we want to get the formulas of each of those products first. Then we can look at our equation and balance it. And then once we have that, we can start to get the ionic equation, and then ultimately get the net ionic equation. So if you want to practice with these ones, just pause the video, but I'm going to start just working through the first one. And like I said, we're going to be getting the products, so we'll actually wind up with sodium chloride and then barium sulfate. So we'll have BaSO4, because barium is going to be +2, sulfate is going to be -2. And you'll want your reference sheet for this one so that you have the charges on some of these polyatomic ions, as well as the solubility rules, so that we can identify that barium sulfate is going to be an insoluble precipitate. So that's going to be a solid. Whereas the sodium chloride, again, like I said, we'll put the 2 out in front, because now that balances the reaction there. But this is our molecular equation. So if we want to then get the ionic equation, we need to look at these aqueous solutions, figure out what ions they're going to dissociate into. So barium is going to be +2, chloride -1, sodium +1, sulfate -2. And then you'll notice when I do this, we've got 2 chlorines here. Each of them are going to be -1. So when we go to get the ions, we actually break out the subscripts and put it as the coefficient now. But with something like sulfate, since that SO4 is the polyatomic ion itself, we don't have to change that at all. But with the sodium as well, we've got 2 of those sodiums, but each of them are +1. So that's why we put the 2 out front there. But with the right-hand side, we've still got sodium and chlorine. So that's why we're going to be able to remove those from our ionic equation and just focus on the barium and the sulfate for the net ionic equation, because those are going to be the only 2 ions that are actually changing. So in this case, the sodium and the chlorine would be our spectator ions. And then with the second one, we've got to do the same thing. So we're still going to have one of those metathesis reactions, double replacement. So we'll combine copper with carbonate, potassium with nitrate. And then since potassium's +1, nitrate's -1, we can just have those make KNO3. And we'll put a 2 out in front just because we've got 2 nitrates and 2 potassiums on the left. And then with the copper 2 carbonate, each of those is going to have a charge of 2. It's just plus and negative for copper and carbonate respectively. So we'll also just wind up with a formula of CuCO3. So then when we go to get our ionic equation, we'll have both of those initial solutions dissociate. So we'll have all ions on the left, but copper carbonate is going to be our precipitate on the right. That's going to be insoluble. So when we go from the ionic to the net ionic equation, we'll just remove potassium and nitrate from both sides. And that's why we've just got carbonate plus copper. It doesn't really matter which way you have them ordered on the left-hand side. So if you want to put the positive ion first, you can. But we're just showing that we're taking those 2 ions, combining them to form this insoluble precipitate, copper 2 carbonate there.